Yeah.
Please read the following text taken from.
Another chart?
What?
Another chart, dude.
Oh, yeah, amazing.
Bro, oh my god. This man and his charts.
Charts, bro. Charts. I mean, look, bro.
Wait, do you guys have it yet?
Hey, what
Wait,
the
okay.
charts?
Okay.
There's so many of them.
This one in particular? Oh, this one too, obviously.
Wait, so we have to scan this and turn it in?
Eventually. Yeah.
What the hell?
You should
That's
take
a lot of scanning.
That's too many.
And we have to unstaple them to scan them.
So why'd you make us staple
Are
in
you
the first
serious?
place? Literally for nothing.
Why do we have to unstaple them?
That doesn't make sense.
Yeah, I don't know. Just like, dang, I just cannot take a picture of my
What is it? Like geometry.
Why are there so many samples? It's just out of order. Morgan, you're out of
Molecular
order.
What happened?
geometry.
You're not in the same order as the page on the packet.
Well, and actually,
Oh, yeah.
the title of the
Yeah.
second one is partially on the first page and partially on the second.
I'm
What is that
uncomfortable
say?
with
Bond
all of
angles.
that. Look. Why did you set it up like this?
The fuck is always at 60, 60, 60, am I right? This is an equilateral triangle.
Alright, so list thought structures, we'll do several examples on here. I have other examples as well, but we'll at least get you a guide here, kind of, if you're looking at it, kind of your notes. Okay, let's do BEF2. That is beryllium difluoride. And there's an area on the very back, I think, that I left you some blank spots, did I not? That you can use. Yeah, the blank areas, so you can do beryllium difluoride if it's not there. Yep. But is it not the first one?
It's not the first
Oh, I
page.
think I found it.
Oh, okay.
No, that's-
No.
Oh,
That's not it.
falling.
Oh, you're doing the very
Is
bottom
that the
one.
same
No,
chart?
that's not.
Yeah.
Where is
I think
it?
so.
It's on the back.
Okay.
You're doing the
There's
very
like
bottom
translucent.
one.
It's the very bottom one on the
Okay.
first one.
Yeah.
So wherever it's at, beryllium
Little
Oh.
hairs.
Okay. We will learn the systematic way to name things, but that's coming up. So for now, I'll just name it for you, and we could talk about it later if we need to. So beryllium difluoride. All right. When you look at this, we need to account for the total number of valence electrons for beryllium. How many?
2.
Because it's in group
2A.
2A. And then each fluorine has 7 valence electrons,
That's 14.
and there's 2 of those. So the total number of valence electrons.
16.
Okay, 16 electrons. What you're trying to do here is legitimately help try to ensure that the total number of valence electrons is divisible by 2. That just means electrons will end up being paired. Is that a have-to scenario? No. That is in no regards to true science. It's just for us, most of the examples we do are going to be even quantities, even integers of the value of 2. Okay? That's the first good general check mechanism. The Lewis dot structure has a couple steps to it, and I'll try to keep track of the steps, maybe over here by the lattice structure. We'll move it. All right, Lewis dot structures determine the number of valence electrons. So how many of those do you have? The second step would be determine the central atom. So what atom is going to end up going in the center of that structure? Place the valence electrons around the atoms. It's more stable for electrons to be paired than it is to be apart, so pair unpaired electrons. So unpaired need to move to paired, which means in essence you're creating single bonds. And then the fifth thing, and kind of the last thing, is check for the stability of a noble gas, either through achieving a duet of electrons like helium or an octet of electrons like most other noble gas configurations. Yes, we will have exceptions here, but we'll deal with those when we come. So let's say satisfy the octet. By creating double or triple bonds. Do you have to do it this way? No, but is it just a method? Sure, absolutely. It'll work for us as well. Okay, how do we decide what the central atom is? One of the ways you can do this is by looking at which atom shows up the least number of times in the chemical formula. Oftentimes, that's the central atom. So if we go ahead and put beryllium in there, we put fluorines on the opposing sides, then this is the central atom, and these would now be considered the bonding atoms. Now notice what we have going for us here is we're trying to draw a Lewis dot structure for something that is an ionic compound. So what we need to kind of tweak out is, should these actually end up being covalent bonds in here, or are they really just stabilized by those electrostatic forces? So after we draw it, we'll come back and clarify which is which. But we know that that's the central atom. Place the valence electrons around beryllium. There's one, there's two, right? So those are 2 electrons of berylliums. And then fluorine has 7. 1, 2, 3, 4, 5, 6, 7. Same thing for this fluorine as, well, 7 there. Okay. All right, so that takes care of steps 1, 2, and 3. More stable to be together than it is to be apart. However you draw this, we are going to change it. I'm going to go ahead and put a single bond in here now. We don't want that to be a single bond, but just to prove a point here. And then check for the octet rule. So does fluorine have a octet of electrons around it? 2, 4, 6, 8, because those look like they're being shared. 2, 4, 6, 8, those look like they're being shared as well. What about beryllium? No. So now the question becomes, should beryllium be stable with a total of 2 4-valence electrons around it? Because currently we're showing this as a covalent molecule that's sharing electron density. If that's true, we might be able to suppose that the electronegativity value of fluorine is so incredibly high, it wants the electron more than any other atom on the periodic table, that fluorine will not take these electrons, move them in between beryllium and fluorine to share like that, right? Because doesn't fluorine still have the same number? We just said, instead of being here on fluorine, come here. Spend more time here, isolated between beryllium and fluorine. We could argue, potentially, that fluorine doesn't want to do this either, right? Now, though, however, wouldn't beryllium have an octet of electrons? Okay, so it's not going to do that because fluorine wants the electrons more than anybody else. It's not going to share more than it has. So let's go ahead and move those back to here. And the same thing with these as well. Now let's deal with the fact that we're violating the octet rule, but it's not actually a covalent compound. It is an ionic compound. So therefore the electrons cannot be shared between beryllium and fluoride. What's going to occur now? Complete transfer. Beryllium is the lesser electronegative atom. Fluorine is the greater electronegative atom. So therefore, fluorine wants them, beryllium wants to give them up. And when you do so, you form fluoride and beryllium ion. So 2 fluoride ions and a beryllium ion. Beryllium has given up 2 electrons, therefore it's a positive 2 oxidation state. Fluoride has gained 1 electron, therefore its oxidation state is a negative 1, and you have 2 of those. So these electrostatic forces of attraction occurring between 2 oppositely charged particles is what's stabilizing the ionic compound. Then you would draw the lattice structure for beryllium difluoride as well. So we forego the bond character here in terms of like developing a single bond and call it an ionic compound that's stabilized by those forces of attraction. How many, as a general question now, we have how many valence electrons for fluoride?
8.
Right?
8.
How many for beryllium? No trick question.
2.
How do you know? You're right. Yeah, there you go, perfect. Beryllium is in group 2A. It has 4 total. If it gives up 2, it now looks like helium, and helium has 2 electrons in its outer shell. It's only 2. So it has 2 valence electrons. Is that okay? Have we satisfied the stability of a noble gas? Absolutely, because helium isn't an octet, it's a duet of electrons in essence, right? So helium would be okay there. So we've fundamentally kind of walked through these steps, but rationally looked at it as an ionic compound, and we still developed the correct Lewis dot structure for an ionic compound. Okay. All right, let's go here. Number of lone pairs around the central atom. Does the central atom have any lone pairs around it? I don't see any dots happening around there, so we're going to go ahead and do 0. Does the number of regions, and we'll call them bonding in this scenario, true ionic compound, right? But how many atoms are bonding, if you will, interacting with beryllium? There are two different regions. This, I'll circle it, is one region where those ions will interact. This is another region where those ions will interact. Fair? Nothing too crazy there. So if we have 0 lone pairs, 2 regions of bonding, the electron pair geometry is going to be called linear. Now, linear molecules, if you're remembering them, look like... I got it. This, there, where there's the beryllium, there's the fluoride, these single bonds are not actually there, right? They're just electrostatic forces of attraction. And now we have to deal with, why is the fluorine atom not allowed to do this? Or allowed to do that, right? Or why can the whole thing not be bent in some dimension? That's VSEPR. There is a city right west of Salina that's called VSEPR. Aha! When we lived in Colorado for 8 years and we'd always come back a couple times a year, after you've been driving for 8 hours and you hit that, I took the opportunity every time to tell my wife about VSEPR. Felt like it was a good car conversation. It is the valence shell electron pair repulsion theory. Boom, there it is. Valence shell electron pair repulsion theory, VSEPR. Okay, now VSEPR says this. VSEPR says, consider the highest energy electrons. Okay, those are the electrons in the valence shell. Fair? So it takes care of this first part of the word. And they're paired up. They're going to orient themselves in such a way as to lower the potential energy by maximizing the distance between them. Okay, one more time. The valence shell electron pair repulsion theory says we want to maximize the distance between valence electrons in order to lower the potential energy. And what does that do to stability? Increases the stability. That should not necessarily be counterintuitive. If I say an electron is negative and an electron is negative, and if you bring them together, aren't they unstable? Like negative charges repel. So it's more stable for them to begin to be apart at some distance. You don't need to redraw this curve. It's been it showed up in your notes probably. You can if you want to, but it's shown up in your notes multiple times. We had something like this, where we're looking at the internuclear distance between two atoms, atom 1, atom 2. As you bring those atoms together, it takes energy as the nucleus begins to repel and as the electrons begin to overlap. Then you begin to part, you relax. But then if you want to keep stripping them apart, they actually kind of want to be together. Okay, that's this energy curve. This optimal distance is what we're talking about here. What is the maximum distance? So that would be here on this axis, that you would achieve the lowest potential energy, there it is, and the greatest amount of stability, okay? So that's Coulomb's law, among other things. Even some physical realities of the universe can be choreographed that way as well. So we need VSEPR. So go back to here, this is our model. Why can I not bring this fluoride closer to this beryllium atom? Why can I not bend that? Yeah, because there's electrons in fluoride still, and we still have some electrons in beryllium. Howdy. Thanks. Appreciate it. Nice. Okay. Then you would begin to take these electrons and repel them from here. All right? And as they begin to repel, this guy wants to go back, and it relieves the pressure, the force. And then it begins to go this way, but then it's repelling across the electrons again in the purple as well, and it goes back, right? And then eventually you just get this perfect position. Are these constantly moving? Absolutely. They're going this way as well. They're going this way additionally. This is not a stationary object. But you can see how maximizing the distance between valence creates a linear shape. It doesn't matter how you hold that in 3 dimensions. You always get a linear arrangement. So here's what we say. We say the electron pair geometry really represents the regions around the central atom. When you have 2 regions, you call that linear, 100% of the time for us. However, if both of those regions are bonding, meaning you have no lone pairs around the central atom, then these 2 words are going to end up being the same. I like to think of this as if I had a camera and it had a filter, and the filter on the camera only allowed you to see the electrons here and here, or the electron density, then the camera would show you 1, 2. And it wouldn't care. It still would be 1, 2. It still would be 1, 2, right? 2. It's linear. This camera filter would be, it can't see any of the electrons. All it sees is the atoms. So it sees white, purple, and white. And then in 3 dimensions, what shape does that look like constantly? It's linear. So this is more of where are the atoms at. This is what is the electron density being distributed around the atom look like. What's the bond angle there? Atom to atom to atom. Atom to atom to atom. Sorry? Yeah, atom to atom to atom. 180. Because this is a circle, right? And it makes a complete circle. You have angle 1 and you have angle 2 here. So 2 angles bisecting a circle, 180 degrees. Yeah, question?
Yeah, so you said that they're being held together by, I don't know,
Static forces? Yeah.
electrostatic
Yeah.
forces.
Yep.
So what does that mean, like, if something else with a similar, I don't know,
Yeah.
I guess, negativity or electron, like, configuration or fluorine, which it already has an additional electron, can it replace fluorine? Is it like?
Yeah. Yeah, so tell me if I'm not answering this. If we substitute this out for like iodine or something, would the same thing occur? If it's a halogen substitution, which probably 100% of the time, it's probably unlikely that a halogen is going to share more electrons than it has to. However, iodine, further down, has a lesser desire for the electron. So iodine compared to fluorine, for sure, iodine would rather share the electron compared to fluorine would. So it's more likely that iodine might make a double bond than fluorine would in that situation.
Okay, so is that also the reason why fluorine would stay rather than being switched out with iodine? Because
Yeah, to your point, and kind of as a separate note, we are gonna go there, but not necessarily today, so just as a small segue, you don't need to write it down, but just to prove the point. If chlorine is stabilized by a positive oxidation state interaction, right? So this is an actual compound. If you introduce an element that wants the electron more, doesn't fluorine want the electron more than chloride does? You with me on that?
Yeah.
It's higher up. So chlorine has it, fluorine's gonna take it, and when fluorine takes it, it turns into fluoride, and chlorine loses it. So you actually take fluorine and substitute it in for chloride to produce fluoride in chlorine gas. This is called the oxidizing strength of halogens, and it is something we are going to show and talk about, just not today. Yeah, good. Okay, for Monday,